Hi, and welcome to Week 5. We will review Chapter 2 and begin our introduction to Chapter 3 about infinity. Let's review Chapter 2. Chapter 2 quiz will need to be taken online before Sunday the 16th at 11:55 p.m. and the password will be given at the end of this video. Section 2.1 wants you to look at the world in a quantitative way. For example, looking at the pigeonhole principle. Suppose we have an incoming freshman class in the fall of 500 students. Do we have at least 2 people who share birthdays, just considering month and day, not year? We know for a fact that at least 2 people share a birthday. We do not know if 2 or more people share a birthday, and we do not know what day or what people. We do know for a fact that at least 2 people share a birthday because there are more people than possible days of the year. The Fibonacci sequence, looking at your screen, you see 1, 1, 2, 3, 5, were built by adding the previous 2 terms. Unique things about the Fibonacci sequence, they're found in nature. Every natural number can be expressed as a sum of non-adjacent Fibonacci numbers, and the ratio of adjacent Fibonacci numbers oscillate bigger and smaller around the 1 plus square root of 5, all divided by 2. You can see a table in your book. Next, Fibonacci NIM. Read the winning strategy under Fun and Games with Fibonacci. Make sure the initial number of sticks is not a Fibonacci number. Make sure your player 1, write the number of sticks in the pile as a sum of non-consecutive Fibonacci numbers, and remove the smallest number in the sum you found. For example, if the pile originally has 11 sticks, you could rewrite 11 as 8 plus 3, both Fibonacci numbers that are not next to each other. Since 3 is the smallest number in the sum, the winning strategy would have you take 3 sticks from the pile. 2.3 has us looking at prime numbers. Is 217 prime? How could we check? If we took the square root of 217, we would find that it is approximately 14.703. Double check ourselves. 14 times 14 is 196. 15 times 15 is 225. And yes, 217 falls right in between these numbers as we would expect. Now we know we have to check all the primes up to 14, which would be 2, 3, 5, 7, and 11. Recalling the rules for divisibility, we do not even have to check some of these numbers. So, let's take a look. 217. Do we really need to divide by 2? No, 217 is not even. Do we need to check 3? No, 2 plus 1 plus 7 equals 10, not divisible by 3. Do we need to check by 5? No, 217 doesn't end in 0 or 5. And really, we don't even need to check 11. 20 times 11 is 220, which is too close to 217 to worry about. So all we have to check is the prime number 7. And in fact, when we divide 217 by 7, wow, we find that 7 times 31 is equal to 217 evenly. 217 is not prime. 2.4 has us looking at modular math. Just remember, remainder, remainder. As we look at the clock rotations or cycles, we are really thinking about equivalents. 14 mod 6, you should be asking yourselves, how many times will the clock spin? How many groups of 6 can be removed from 14? 2. 6 times 2 is 12, so the clock would proceed past the top and land on 2. And 14 subtract 12 would leave us with a remainder of 2. So 2 is equivalent to 14 mod 6. The rest of 2.4 has us looking at UPC labels. And for the purposes of this class, you want to remember that your final answer, your goal would be to have 0 mod 10. That is, to find numbers that are evenly divisible by 10. So 10, 20, 30, 40, 50, numbers like that. Always start by multiplying the first digit by 3 to get a product. Add the product plus the second digit. Multiply the third digit by 3 and get another product, and then add it to the previous 2 that you had already found. You repeat and you repeat until you come all the way across and you add the last digit. Your answer should be a 0 mod 10 number if the UPC label is valid. We skipped 2.5. Now looking at 2.6, it'll be important for us to know the definition of rational numbers and the definition of irrational numbers. Rational numbers can be written as a fraction, a over b, where b does not equal 0. In other words, we can't write a fraction with 0 in the denominator. And the decimal either terminates or repeats with a pattern, such as 1/3 is 0.333 repeating. The definition of irrational numbers is simply not being rational, therefore it cannot be written as a fraction, and irrational numbers have decimals that go on forever, unending, without a pattern. Examples of this would be square root of 2, pi, something like that. Now, beware, not all prime numbers written in the form with the radical sign are in fact irrational, such as the square root of 4, the cube root of 8. Because they can be simplified to be the number 2, they are considered rational. They can be rewritten as a number that qualifies as a rational number. The last part of our review is 2.7. Real numbers are both the rational numbers and the irrational numbers. And we learned in this section how to convert a repeating decimal, which we know is rational, into a fraction. So let's review that first. Let's use some algebra and start by setting n equal to 4.151515 repeating. Now, if n is equal to 4.1515 repeating, we need to find the pattern. The pattern is 15. So think about what number in the power of 10, so 10, 100, 1000, would we need to multiply n by so that we have the pattern beginning again after the decimal. Look at 100. 100n is equal to 415.151515. 10 didn't work because it gave us 45.515151, changing the pattern. The next step would be to subtract n from each side and the equivalent for n on the other side. So 100n, subtract 1n, 415.151515, subtract 4.151515, we notice that all of the numbers to the right of the decimal become 0, 0, 0, 0, 0, unending. We are now left with 99n on the left-hand side and 411 on the right. To solve for n, we divide each side by 99. So we have 1n on the left-hand side, and we have an error in the movie, so please note that on the right-hand side, that should be 411 divided by 99. 411 over 99. The second part of 2.7 is reviewing how to go from a fraction back to a decimal. And yes, that's long division, just like your 4th grade favorite memory. So there's an example of long division provided here on the slide, and I will not go over it. But once it begins to repeat, you can end your long division. Well, that wraps up our review for the Chapter 2 quiz. As always, if you have any questions, please contact me. Now, Chapter 3, 2 sizes of infinity. Really? How come we've kept it a secret from you? You'll find out in sections 3.1 through 3.3 that we cover over the next 2 weeks. 3.1 is oversimplistic, so do not overanalyze it. It introduces the idea of infinity by reminding us how to compare sizes as we did as youngsters. As youngsters, we couldn't count, but we always knew which pile of candy was larger than the other. So how did we do it? We simply started by taking one piece from each pile and pairing them up. That is called one-to-one correspondence. If we ran out of candy in both piles at the same time, the piles were equal. If one had candy left over, that was the larger size. That's the idea that you are going to apply to your 3.1 homework. In 3.2, the idea of one-to-one correspondence that we just learned in 3.1 is setting you up for a way to think about infinity. Remember, finite versus infinite is a different way of thinking. We have to get rid of our ways that we use our brain in finite and open our minds to a new and exciting world of infinite thinking. Look at the set of numbers below. The natural numbers, 1, 2, 3, 4, 5, 6, and so on, compared to the even numbers. Do you think that those sets are the same size? Or do you think the even numbers are in fact half the size, missing all the odds. What do you think? Take a moment to just think. Are the natural numbers the same size of set of numbers as the even numbers? Well, what do you think? Did you use the one-to-one correspondence? Can you match a number in the natural numbers with an even number and pair them up? Yes. In fact, look at the red lines. The 3 dots at the end of each set indicate that we need to use an infinite brain, the one that looks at things differently. We look at it by using one-to-one correspondence. They don't have to match a 2 to a 2 or a 4 to a 4. Simply matching a number in the natural with a number in the even numbers allows us to see that the pairs would go on forever, unending, and in fact, those two sets of numbers are the same size. Even though our brain tells us the odds are missing, we now know that those two sets are the same size of infinity. I'll end this week with a classic cartoon, with I telling Pi to get rational, and Pi telling I to get real. The password for the Chapter 2 quiz this week is Get Real, all one word, all lowercase, GETREAL. Have a super week.